This is a classic ballistic pendulum problem. We've got a bullet moving towards a block. The block is sitting on a frictionless surface, and it's attached to a spring. The bullet embeds itself into the block, and at some later time, the block comes to rest and the spring is at its maximum compression. So I can see right off the bat, I've got an inelastic collision here. I know it's inelastic because the bullet is embedded into the block. The two objects become one. So I can't use energy to get through this collision, so I'm going to have to use momentum to get through the collision. I can use energy to figure out anything that happened before the collision. In this case, nothing happens before the collision. So I'm going to call time 1. I always do this when I get a problem like this. I split it up into some block of time prior to the collision and a block of time after the collision, and then going through the collision. So I'm going to call my time 1 here what the split second before the collision, time 2 the split second after the collision, and time 3 some time later when the spring is at its maximum compression. So the first thing I know here, I'm going to need that spring constant eventually, so I'm just going to solve for it right off the bat. And they give us some information. The force of a spring is equal to kx. They tell us the force, and they tell us the compression, and I get my spring constant is 300 newtons per meter. Don't forget to convert those centimeters to meters. Okay, so I'm going to need that later. We're asked to find v1, the initial velocity of the bullet prior to it hitting the block of wood. And we're going to work backwards through this problem because we're given information at the end. We can work our way all the way backwards through the problem. We're going to go from 3 to 2 using energy conservation. And we're going to go from 2 to 1 using momentum conservation. And then we'll have our initial velocity. Okay. So I'm going to start off with the energy at condition 3 is equal to the energy at condition 2, and I can say that because there's no friction. And at condition 3, all the energy is stored in the spring, and at condition 2, the spring has not started to compress yet. The block is at its maximum velocity the instant before the spring begins to compress. So all the energy there is in kinetic energy. And I'm going to go back and show you one more thing here. The mass. So in condition 3, I just have a spring constant and I have a compression distance. But at condition 2, I have a mass and a velocity squared. The mass is the total mass, right? That's the two objects have become one at this point. So it's the sum of the two masses. And it's what I'm calling V2. That's the mass at this point. That's the velocity at this point, sorry. So I end up with 1/2. I've got my 300 newtons per meter, that's my K. I've got 0.15 squared, that's my compression. And 1/2 the mass of the bullet, 0.008 kilograms. The mass of the block, 0.992 kilograms. V2 squared. and I got 2.60 meters per second for the velocity of the block plus the bullet at time 2. That's not what we're interested in, though. We are interested in the velocity of the bullet prior to hitting the block. So we have to go from 2 to 1 using momentum conservation. We have to get through that collision. So I say the momentum at 1 is equal to the momentum at 2. M1 V1, that's the entire momentum at condition 1 because the block is stationary. And at the end we have the two objects moving together at velocity V2. And let's see, I plug everything in. 1. I got 325 meters per second. So just a real quick check here. We have a collision, so you should be thinking momentum when you have a collision. We're given that something happens after the collision. So I always pick a time. I'm calling it time 1, just the split second before the collision, time 2, the split second after the collision, and then time 3 later on in the problem. And then in this case I had to work backwards through the problem because of the information that was given and what was asked for. I had to work backwards through the problem.